Okay, so last time we have started with full wave center tap rectifier with resistive load, and here is my circuit. So compared to half wave rectifier, it has two diodes. Each diode works in a particular half cycle and maintains the current direction same in both the half cycles. That is why the output waveform is full wave rectified. That means in both the positive or negative half cycle, we get a positive wave output. Alright. So basically, during the positive half cycle, output follows the input. During the negative half cycle, output follows the negative of input. Alright, output is following the negative of input. Alright, and in first case, which two diodes are on? In first case, when this is positive half cycle, which diode is on? D1. And in second case, diode D2 is on, and so on and so forth. So if you can see, the average value of this waveform is always positive. Now, the nature of output current is also of the same nature as output voltage. Why? Because it's a resistive load, so there is no phase shift between input and output. So they are having the phase shift same. What about the height? Height is, instead of Vm, it is Im, which is V out upon RL. So height wise is different, magnitude wise is different. Of course, the average value again will be positive. So up till this we have completed, and also I guess yesterday's lecture we have also plotted the voltage across the diode D1 and D2. Correct? So that is available in last lecture handout. So today we'll start with the derivation or analysis of full wave rectifier with resistive load analysis. So first we'll derive the expression for rectification efficiency, which will tell how efficient your rectifier is working. Then we'll calculate the expression for ripple factor, then expression for TUF, that is transformer utilization factor, that will cover together for all three rectifiers. All right. So let's start with the V out average or average output voltage. Now, since we have done the derivation for half wave rectifier, I'm not repeating the steps again by writing. I'm going to show you all how the final step comes. So what you can do is you can write down the average value final expressions. No need to write the complete derivation. Okay. So let's analyze this waveform. For this waveform, we have to find the average value. So tell me first of all, what is the time period when the waveform repeats? It will repeat after pi only, correct? So my total T, capital T is pi. Alright. So what is the definition of V out average or VDC? It's 1 upon T, 0 to T, V out of d omega t. Alright. And what is my V out? Here, why I have written 2 pi? It's pi, right? So is it 2 pi or pi? It's 0 to pi only. Okay. So VDC is 1 upon pi integral 0 to pi Vi of output is same as input. Okay, here it is in the positive half cycle. So Vi of omega t is Vm sin omega t. So 1 upon pi integral 0 to pi Vm sin omega t. Vm is a constant, and what is integral of sin omega t? Minus cos omega t. So where omega t is going from 0 to pi, and we have Vm upon pi outside. So here we take the minus sign outside. Actually, this should have been like this. This is into. Okay, because this will be treated as if we are subtracting it. So your cos phi will be -1, cos 0 will be 1. So inside you have -2. So this minus sign gets cancelled. So what you will get? 2 Vm upon pi. So last time, if you remember, in half wave rectifier it was Vm upon pi, right? Here it is 2 Vm upon pi. So write down the average value of output, V out average or VDC is 2 Vm upon pi for full wave rectifier. For short form, you can write FWR. But in the exam, you write the full form, please. So for a full wave rectifier, the average value is 2 Vm upon pi. And if I convert it into a number, 2 upon pi, if I do, it will be 63.6% of Vm. Last time it was half of it. Have you written the formula 2 Vm upon pi? So that means if I have this output value, okay, this part over here, entire height is my AC, and my average value is 0.636 times Vm. How this number came? 2 upon pi you do, you will get 0.636. So my average value is, average DC value is 63.6% of maximum value. So what is my output of this full wave rectifier? It's a pulsating DC. That means it contains AC as well as DC component, both. It's not a pure DC. It's a pulsating DC. All right. Can I move on to the next one? Okay. Next, we need to find out the output current, average output current. Some books they also call it load current, IL, current flowing through the load. That is same as output current only. So I out average will be, since it's a resistive load, there is no phase difference between voltage and current. So I out average will be V out average upon RL. And what is V out average? VDC upon RL. And what is my VDC can be written as? VDC is 2 Vm upon pi, right? So 2 Vm upon pi into RL. And what is Vm upon RL? Im. So we can write it as 2 Im upon pi. Okay. So both the formulas are there. Or basically we can also say V out average is I out average into RL. So that is also true. So please write down the formula for I out average, 2 Im upon pi, where Im is Vm upon RL. I out average. Okay. Right. Okay. Now next we find the RMS value of the output. What is RMS value? RMS value of the AC component. RMS value, it's not of DC, of the AC component. So how do you define it? V out RMS, it's 1 by T 0 to T, V out square omega T d omega T, the whole raised to half. Okay. And here we have, this goes from actually 0 to pi. So here I'll write it over here till pi. 1 upon pi 0 to pi vi square omega t d omega t raised to half. Don't write this derivation, just listen to the final expression how we get it. So we take 1 upon pi outside. So sine square, what is the integral of sine square omega t? Basically sine square omega t will be 1 minus cos 2 omega t divided by 2. Okay. So this Vm also we take it outside this integral because it's a constant. Then we'll get Vm square upon 2 pi. 2 also will take it common outside. So we get omega t. What is the integral of 1? Omega t. Okay. Then integral of cos will be sine. So sine of 2 omega t by 2. It should be by 4, right? Yeah, it should be by 4. Because, yeah. Okay, yeah. We have to only took 2 outside. So that's why it's sine 2 omega t by 2. That's correct. Okay. Now here we substitute omega t going from 0 to pi. So first step omega t from 0 to pi will be pi minus 0. Then it will be sine 2 pi upon 2 minus sine 0 upon 2. So sine 2 pi is 0. Sine 0 is also 0. So what you will left out is Vm square upon 2 pi into pi. So that will be Vm square upon 2 the whole raised to half. That will be Vm by root 2. Remember in case of half wave rectifier we got Vm by 2, right? Or Vm by root 2 only we got. Vm by 2. So in this case it is Vm by root 2. Write it down. RMS value of full wave rectifier output will be Vm by root 2. Vm by root 2 for full wave rectifier. Okay. And what about I out RMS? I out RMS is Im by root 2. And what is Im? Vm upon RL. So I out RMS is Im by root 2. Completed? We can write in short form instead of V out RMS, VRMS. Instead of I out RMS, IRMS. It means the same only. Now, we got the expression for V out average, I out average, V out RMS, I out RMS. Next, we'll find rectification efficiency. So write down the heading rectification efficiency. Write down its formula again. I mean, you write this completely. Rectification efficiency is a new term, so you calculate this together. So write this down. Rectification efficiency is output DC power upon input AC power into 100. Okay, it is defined as the ratio of output DC power to the ratio of applied input AC power. Okay, now what is DC given by V out average into I out average, or VDC into IDC? So it are three formulas: VDC square upon RL, V into I, V square by R, and I square R. So these three formulas are valid. AC will be V out RMS into I out RMS, or we can call it V RMS I RMS. It's also V RMS square upon RL and I RMS square into RL. All the three formulas are valid. I'm using the middle one. So PDC, you can write from here. PDC will be VDC square upon RL. What is VDC for full wave rectifier? 2 Vm upon pi, right? The whole square. So if you open the bracket, you will get 4 Vm square upon pi square RL. So this we call it equation number A. PAC will be VRMS square upon RL. What is VRMS for a full wave rectifier? Vm by root 2. So it will be Vm square upon 2 into RL. Expression number B. Now what we need to do, simply divide them. So PDC upon PAC, if you divide them, you will get out, you will cancel out most of the terms, and you will get 8 upon pi square into 100. And if you check out in the calculator, it will be around 81.05. So please check this and write this derivation. But this is something new which you are doing. And if you notice, the efficiency has doubled when you go from half wave to full wave. You remember, in the case of half wave, it was 4 upon pi square into 100. Here it is 800 upon pi square. When will you answer this question in exam? When they ask you directly, derive the expression for rectification efficiency for a half wave rectifier. They ask you these questions. Do you want me to give you all the type of questions which can be asked from theory modules? Okay, I'll give it to you for this module at least. Okay, also for module number 5. I'll give you the handouts as well as the, it's the range of questions which can be asked. Same question can be asked in 4 different ways, but no numericals in this. Okay, so did anyone check 800 upon pi square? How much it is? 81.05. Yeah. So what is the major learning over here? That the rectification of full wave rectifier is better than, actually double than, your half wave rectifier. So in practice, we don't use half wave rectifier. I think you have done mobile battery charger in your labs, right? Which circuit you have used? Full wave bridge rectifier, which efficiency is also same. Completed? Now next, ripple factor, its definition we have done it last time. And you remember we have written this formula? IAC upon IDC square root of IRMS square upon IDC square minus 1. This will be the common formula for all the derivations. So here, our ripple factor will be square root of IRMS square upon IDC square minus 1. Write down this. And for a full wave rectifier, we can write. And write down the final formula. IRMS is Im by root 2. IDC is 2 Im by pi. So if you simplify it further, you will get R as 0.483. In case of half wave rectifier, it was 1.21 now. It was 121%. Here it is 48%. So reduced. The lesser the value of R, the better is the rectifier circuit. Full wave center tap rectifier. Okay. You have to just substitute the value of IRMS and IDC. You will get answer as square root of pi square upon 8 minus 1. Someone please check if it is 0.483. Yeah, good. So what it means that it contains the full wave center tap rectifier contains the smaller AC component at the output compared to a half wave rectifier. So half wave rectifier is not practically used. Full wave rectifier is used. Okay, done? Completed? I told you now that the transformer utilization factor will cover for all rectifiers together. Completed everyone? Yes? Okay. So next I'll start with full wave bridge rectifier. Remember, all the expressions which I have shown you right now are same for full wave bridge rectifier. What is differences in the circuit diagram? So it doesn't have a center tap transformer, it has a normal transformer. So right on the topic, we will be discussing the circuit diagram, working and the waveforms. Analysis, it's remaining the same. So let's start drawing, write it down. Full wave bridge rectifier, draw the circuit diagram. Full wave, all I have studied Wheatstone bridge, right? Kind of a rhombus and attach all the four legs, so it's like bridge rectifier. So what does it do? In a crude manner, if this is my full wave bridge rectifier, if I have the secondary voltage of the transformer over here, what it will do to the output? Let's say we have 2 cycles. It will do it this way. Okay, you will get a pulsating DC at the output. If this is AC, you get a pulsating DC. That is what full wave bridge rectifier will do. Now let's come to the circuit diagram. This was the concept. Okay. Now let's draw the primary and the secondary winding. So first of all, draw the transformer. Let me expand it. Oh, I want to use black color. Okay. Here is my AC mains. Then I have a laminated core. Then I have a secondary windings. Should be less or more or same. I have to using a step down transformer, right? So it will be less. Okay. Then you can form kind of a bridge over here. So what will come over here? Glass will be connected like this. Kindly draw this. So we have 2 choices whether to draw the resistor over here like this. Let me draw the resistor over here with green color. Okay, and here is my ground. Now this ground and this ground is different. They are isolated. I told you all that before. So this is my AC mains. What is this transformer called as? Step down transformer. It's not, as you can see, it's not center tap. Step down transformer. Let me call these diodes as here it is D1, D2, D3, D4. What is this voltage called as? Let me this point called as A, B, and this secondary voltage is called as VI. Okay. So this is my circuit. I have drawn it very small. You can draw it a little big. This load is RL. So what is VI actually? Secondary transformer voltage. So if this transformer ratio is 10:1, if here it is 230, you will get 23 over here as VI. Are you understanding? And assuming that when the diode is on, it is replaced with a short circuit, the voltage across the diode is 0. And when the diode is off, it is replaced with open circuit. Okay. Now, tell me how it will work. So this is my input. If I want to draw input over here, VI, this is how it will look like. So this is my VI. Here is my VM minus VM. Mathematically, how will you write VI? VM sine omega t. It has a magnitude of Vm and frequency of angular frequency of omega. Understood? Have you completed the diagram so that I can start the explanation part? Drawn the diagram? Okay. So here I'll give you a hint. Two diodes conduct together. See, what takes a diode to turn on? A positive voltage on anode and a negative voltage on cathode. Means it should be forward bias. How a diode is forward bias? If I apply positive voltage here, negative voltage here, diode will be forward bias, right? That means it turns on and it will be replaced with a short circuit. When it is off, when negative voltage appear here, positive voltage appear here, diode is reverse bias. We can formally call it off. And when it is off, it offers a very high resistance. Then PN junction in reverse bias, right? Very high resistance. So it's replaced by open circuit. Okay. Now tell me what happens during positive half cycle of the input. Meaning I'm talking about this part. So for a positive half cycle of the input, listen very carefully. I'm using red color to explain now. A point is positive with respect to B, correct? Listen very carefully. A point is positive with respect to B. Now tell me which diodes are on. So this positive AC signal applies over here. Okay. Now will diode D4 be on? Because positive is over here, right? Here we are applying for positive to N terminal. So is it off or on? D4 is off. D1 is on? Yeah. So signal proceeds to it. Now after D1, where it will go? It will go to, can it go to D2? No, because D2 here again it's positive, right? This voltage is appearing. So it will go to the load, RL. Then where it will go? It will go to D3, correct? And then it will go back to supply B. And then directly to A. This is how the signal flows. So during positive half cycle, which two diodes are on? So during positive half cycle of PI, which two diodes are conducting? T1 and D3 are on. Okay, and which two, the other two diodes are off. And what is the direction of current flow? I out flows as follows. It will flow start from A. It will start from A, go through D2, then RL, then D3, and then point B. So A, then D1, RL, D3, B, back to A. Yes or no? Yeah. So this is the direction of current flow during what? Positive half cycle of input. Is this understood? I'm not drawing the diagram again because it will take a little more time. I'll show you the cases, how it will flow. Okay. Now I'll explain the other case. Okay. Yeah. Okay. I need to complete the diagram once more. This is D3. What else is up? Yeah. Now during the negative half cycle of the input, point number A is negative and B is positive. Basically, the other diodes which were off will turn on now. So now tell me, how does the signal flow? This is negative. Okay, wait. Point A is negative with respect to point B. This is negative. So the signal comes over here. Will it go to D1? No. D1 will be reverse bias. It will flow to D4, right? Because negative voltage, right? Or you can start from below also. You can, if you are not comfortable with a negative voltage, you can start from below also. It will flow from B. So from B, where it will go to D2, right? And from D2, where it will go? Will it go to D1? No. It will go to RL. And then where it will go? D4. And then back to A. This is comfortable? So it will start from B, D2, RL, D4, and A. Back to A. Okay? This is how it will conduct. And whenever it conducts, what is my output voltage? So here, if you see carefully in the first case also, the output voltage will be across this RL and this will be plus minus here V out. Output voltage is available over here across the diode, across the resistor. And the current was flowing in the same direction from right to left in both the cases. Okay, so did you understand this? So write down during the negative half cycle of input, during negative half cycle of Vi, diode D2 and D4 are on. See, don't go by the naming, huh? You can connect. I mean, in the exam, you can say this is D1, this is D2. You cannot remember or recollect everything. So from the circuit, you trace it. I am saying D1 and D4, but it can change to your change as per your whatever the way you have drawn. So it start with what can we write over here? B, go to D2, load RL, D4 and back to A. Okay, and here we can say the output is positive. Output part is positive during negative half cycle also. And what do you mean by positive? Current flowing going from positive to negative is considered as positive. Okay, so this is the working. Alright, now what about the waveforms? Did you understand the working? So I'll explain again. During the positive half cycle, point A is positive with respect to point B. So in that sequence, the diodes D1, opposite diodes conduct basically. D1 and D3 are on, and you get the current flow in the circuit, and the output follows the input voltage. Basically, whenever the diode is on, it will be replaced by a short circuit. All right. So I'll show it to you how it happens. Once more in the diagram coming. In a negative half cycle, the role reverses of the diodes. Now D2 and D4 are on, and they will be the ones through which the diode conducts. But the current flow is positive even in a negative half cycle. So output is remaining positive only in both the positive and negative half cycles. So how will be my output voltage? If this is my Vin, okay, let me draw it. Here there is no place. Let me just draw input output waveforms. If this is my input, okay, how will be my output? This is Vi. Tell me how will I draw output V out? First of all, I'll mark these points. Okay, then here also it's positive, here also it's positive. But during this duration, which diodes are on? D3. During this duration, D2, D4. During this duration, D1, D3 are on. Are you understanding? Yeah, that's the only difference. In a full wave bridge rectifier, instead of one diode on, two diodes are on, simultaneously. And there is an advantage to it. There is an advantage of bridge rectifier. And normally in AC to DC conversion, in all the adapters of your mobile phone battery charger or your laptop battery charger over here, normally bridge rectifiers are used in practice, in reality. Okay, it's a very famous configuration. So these are my input output waveforms. What about the current shape? The current shape will be same as your voltage, so it's a resistive load. Is it understood? The working input output waveforms? Yes or no? No, yes. Yeah, I'll show you a better PDF. Yeah, so we have divided this into two parts. This is lecture number 34B. So this is what I was talking about. See, if I disconnect the resistor from there and I connect it like this, it means the same. This is also ground, this is also ground. So during a negative half cycle, it flows from A, D4, it starts from B, D2, RL, then ground, coming out of the ground, D4A. This is how it operates. Okay? And during both the half cycles, output is equal to Vi. During the negative half cycle, input is negative, but the output is positive. So this also I have shown you, right? VI, V out and I out waveforms for the diode. And why the I out waveforms are same, similar nature to V out waveforms? Because it's a resistive load. Alright. So you want to draw anything, please draw it. The input output waveforms. Now the good news is here, V out average, V out RMS, rectification efficiency, ripple factor, all formulas are exactly same as full wave center tap rectifier. For bridge rectifier it's same. The formulas are same because the wave shape nature is same, right? What is the difference? Instead of 2 diodes, we use 4 diodes here. Instead of center tap, we use a normal step-down transformer, which is more expensive. Bridge rectifier are less expensive because center tap transformer are costly, little, compared to normal transformer. So rectifiers are a part of AC to DC conversion. Completed this? Have you understood the working? I'll explain you. I'll give you the separate document. Let me show it to you. So you will require some words to write, right? Can you see this? I've also written from where I've taken it. These are not my words. I've taken it from book only. So I've written the book reference over here. See, yeah, I mean, you can write a lot of things. Don't write the description. Description is for you all to understand. I've explained the working over here. What to write? I mean, I am saying over here very easily. But what to write in exam? Everything is over here. And this document I'll share it with you. Is it okay? Yeah. And here, if I want to plot the voltage waveform across diode D1 and D3 when they are on in the positive half cycle, it will look like this. And for VD2 and VD4, it will look like this. You can interpret it how it happens because we have already done it for full wave center tap, so it's same. We are here instead of one diode, we'll have 2 diodes. That's the only difference. So everything is over here. You can just go through it. All right. Whatever things are not there, I'll cross it. Like this is not there for you all, so I've crossed it. Yeah. PIV rating is there for you. Here I'll explain how it is. So this document I'll share it with you all. So this is just a just thing. V out average will be 2 Vm upon pi. I out average will be 2 Im upon pi. Then V out RMS will be Vm upon root 2, same as full wave center tap rectifier. All the expressions are same. So you want to write, you can write it down. V out average 2 Vm upon pi. V out RMS Vm upon root 2. If you wish to write, you can. The derivations we have already gone through. V out RMS is Vm upon root 2. Rectification efficiency is 81.05. And they do ask in exam, derive the expression for rectification efficiency for a full wave bridge rectifier. So you need to explain. If they ask you the rectification efficiency only, then you need to remember these formulas of V out average and V out RMS. Are you understanding what I'm trying to say? If they ask you the same for 10 marks, then you have to derive V out average and V out RMS also. If they ask you for 5 marks, directly use the result. If you understand the difference between 5 and 10, yeah. Then the ripple factor is also 0.483. That's what I was saying. The analysis part is exactly the same for both the rectifiers. So with this, we complete half wave rectifier, full wave and bridge rectifier, except one point is remaining. What is that? Transformer utilization factor. So write down the heading TUF or transformer utilization factor. I hope you will manage. These were like handwritten things which I have written before. So, I mean, I'll tell you I don't know whether you can see this. Can you read this? Okay. So, TUF indicates, transformer utilization factor indicates how effectively the transformer capacity is used in delivering DC power to the load for a given AC power. Basically, you need to write this formula. DC power delivered to the load divided by AC power rating of the secondary winding of the transformer. So write down this formula. I mean the definition of it. It's important to find the power rating of a transformer, which transformer to use, which rating transformer you use. So when you go to a shop and tell the shopkeeper that give me a transformer, he'll ask you what is the rating, what is the voltage rating, what is the current rating. So that is determined by TUF. DC power delivered to the load divided by AC power rating of the secondary winding of the transformer. So We need to derive the expression for TUF for half wave rectifier, full wave center tap, full wave bridge rectifier, these three. So that will close the topic of 4.1 mostly. Okay? Return the definition. Sometimes they also asked us, derive the expression for TUF for a particular rectifier circuit. Okay. Now just listen. The DC power delivered to the load will be PDC. Can you see these black color things which I have written? IDC square into RL. Okay. Do you know what is the VA rating of a transformer? Transformer में we have AC voltage represented in terms of volt ampere rating. If you go to the market and ask for transformer, they will ask for VA rating. So that is the transformer ka VA rating. So the capacity of the transformer is always specified in terms of RMS value. That is IRMS and IRMS and VRMS. See, transformer will only deal with AC voltage. It cannot deal with DC voltage. Okay, what will happen if you apply a DC voltage to a transformer? It will saturate. That means it will malfunction or even break down. Okay, it cannot it's an inductor basically. Inductor cannot tolerate a constant thing. It should be continuously varying. So transformer only deal with AC voltages. Okay, now AC power rating of secondary winding of the transformer. So power rating of secondary winding of the transformer is given by VRMS into IRMS. Write down. P power of secondary winding is VRMS into IRMS. This black color thing which I have written. Power of secondary winding AC will be VRMS into IRMS. TUF is PDC upon power of secondary winding AC. So that will be IDC square RL upon IRMS VRMS. This is the general formula. Then VRMS, IRMS and IDC will change with respect to rectifier, right? Completed? Equation number 2 and 3 written? Yep. Now, so wait, don't write. This is the interpretation of equation number 3. What is VRMS? It's the RMS value of the voltage at the secondary winding of the transformer. Remember, transformer has a primary and a secondary winding. So we are talking about the secondary winding voltage, VRMS. IRMS is the RMS value of the current that is supplied by the secondary winding. See, primary winding is different, secondary winding is different. In module number 3, you have a module on transformer. So in that, your primary winding and secondary winding are completely different. The voltages are different, the currents are different. That is why we have to stress the point that is the secondary winding RMS value. So we need to find the half wave rectifier TUF. So tell me, for a half wave rectifier, what is my VRMS? VIRMS. That means what is my, this is my half wave rectifier. Can you see this? This is my half wave rectifier, right? We are asking what is my VIRMS. Can you tell me how much it is? See, V out RMS is VM by 2, right? We have derived now. V out RMS is VM by 2. But what is VI RMS? Tell me. Now, for a half wave rectifier, this is my AC waveform and input AC waveform, the secondary of the transformer, and these are my output waveform. Transformer secondary voltage. So, will I get V out RMS like this at the transformer secondary voltage, or will I get it like this? Acha, let me mark. Will I get this A waveform or B waveform at the secondary of the transformer? Alright, this VI RMS will be A or B. Where do you get B? At the output of the load. Barabar, na? Here, what do you get? VIAC. You get the sinusoidal waveform. Correct? Are you understanding what I'm saying? So V out RMS is at the output, at the load. And what is that value? VM by 2, which we have derived. But what is VI of the AC here available at here? So we are asking, what is this value? What is this? I don't know whether it's visible or no. What will be this value? So what is the waveform across the secondary of the transformer? Is it this one or this one, A or B? A, not B. Are you understanding? Is this clear to you? Okay. So we get a pulsating DC. So in a half wave rectifier, transformer will supply a secondary voltage if of a pure sinusoidal nature, meaning over here your waveform will be like this. Are you understanding? And over here your waveform will be like this. That's the difference, right? So what's the RMS value of a pure sinusoidal waveform? Anyone knows? It was asked in the ISC exam also. Vm by root 2. Of average AC waveform, RMS value is what? Vm by root 2, right? So VRMS of the secondary of the primary winding will be Vm by root 2, not Vm by 2. Are you understanding? Or you didn't understand still? This we have derived it before, Vm by root 2 of this waveform. Okay, so write down half wave rectifier. VRMS is Vm by root 2. IRMS is, acha, now tell me IRMS value. This is the voltage. What about the current? Current supplied by the secondary winding of the transformer is a pulsating half sine wave. This way. Current is half sine wave, but voltage is pure sine wave. Okay, so IRMS will be Im by 2, which we have derived already. Because current remains the same, na? Current in a loop remains the same. So current nature will be half sine wave only, half sine wave in the sense this way. Are you getting it? Whereas voltage waveform is available at the secondary is different. See, voltage available at the secondary and voltage available at the load is different. But the current available at the secondary and current available at the load is same. So write down VRMS is Vm by root 2. This is the point of confusion. Huh? IRMS is Im by root 2. Now use that formula. You have no formula. PDC upon VRMS into IRMS. Substitute it over here. So TUF is IDC square RL into VRMS into IRMS. Can you see that red color what I have written over there or no? Inside? Okay. No? Okay. So IDC is Im upon pi. VRMS is Vm by root 2. I have explained you why. IRMS is Im by 2. That also I have explained you all why. So substitute in this and find out the answer. So it will be Im square by pi square into RL divided by Vm upon root 2 into Im upon 2. Please write it fast. We have to just substitute the formulas, that's it. IDC is Im by pi. If you are not writing it down, just write down the split ups. IDC is Im upon pi. VRMS is Vm upon root 2. IRMS is Im by 2. So if you solve it further, what you get is, can I move down? Yeah? Is this complete? I mean, do it fast. We have to complete for full wave center tap and bridge rectifier also. Completed? You only write in detail for this one. Others, I'll just show it to you. So you just listen for others. So after you cancelling everything, you will get TUF of half wave rectifier as 0.287. So write down 2 root 2 upon pi square will be 0.287. Meaning, what is the percentage transformer utilization factor? 28.7%. Rest, 71% is getting lost. Transformer is underutilized in half wave rectifier. So TUF is 0.287. So thank God that you don't have numerical for this. Numericals are very tricky for this topic. You just have the formulas, expressions, that's it. Earlier in the older syllabus, there were numericals on this. Okay, done? Have written it? So what is the meaning I have written over here? 28.7%. That means only 28.7% of AC power that will be supplied to the secondary winding of the transformer will be available at the output as a DC power. But only 28.7% of DC of AC is getting transferred to the DC. Rest is getting waste. So a lot of wastage for half wave rectifier. Okay. Now listen to the explanation of full wave bridge rectifier. You will not write. Only write the final expression. Remaining things are there in this document. Now tell me what is VI over here? What is VRMS over here for this diagram? VRMS कितना है? VM by root 2 or VM by 2? VM by root 2 because again it's a AC. What about current? IM by root 2 because that is the IRMS. IRMS is this way, right? So only that much difference is there. VRMS is VM by root 2, IRMS is IM by root 2. So you substitute everything, rest everything is same. What is IDC? 2 IM by pi that we have derived already. So IDC is different. If you want, you can write it down. IDC is different. VRMS is VM by root 2, IRMS is IM by root 2. Only this much difference is there. And if you substitute it over here, TUF will be 0.81. Matlab, in a full wave bridge rectifier, 81% of AC power is being converted into a DC power at the output. So that's very good. Half wave rectifier is how it is very poor because it was converting 28%. Here it is converting 81% of AC power to the output. So transformer is utilized by 81%. You have written it down? Just write TUF for full wave bridge rectifier is 0.81. Do it quickly, I have less time now. Write down the final expression, that's it. This document I'll share it with you. Okay? You have understood how it has come? Now, for full wave center tap, the story is different. How it is different, I'll tell you. In a full wave center tap rectifier, you have a center tap rectifier, right? The secondary current flows through each half separately in every half cycle, right? Are you understanding? Not the entire coil is not utilized. So during the positive half cycle, only T1 is on, okay? Yeah, it flows through the resistor RL and then back to this coil. So one half of the secondary coil is utilized, not the entire coil. Are you understanding? Center tap meaning the entire secondary coil is divided into two parts. And in each half cycle, each part is utilized separately. Okay? So the secondary current flows through each half separately in every half cycle like this. So if I want to plot the I1 and I2 waveform, it will be like this. For a full wave center tap rectifier. So they are different now. So formulas also will be different for each half cycle, correct? So let me show you all that. While the primary carries the current continuously. Carries current continuously. Meaning the primary winding current will be sinusoidal in nature and the secondary winding current will be split up into two parts. So TUF of center tap transformer will be primary TUF plus secondary TUF upon 2. The average of that you take. So what will be secondary TUF? But secondary winding TUF will be IDC square RL into divided by VRMS IRMS. IDC for a full wave it's 2 IM upon pi. IRMS is IM upon root 2. VRMS is VM upon root 2. Till here it is clear. So secondary TUF it's same. It's same as 0.81. Same as your full wave bridge rectifier. Any problem in that? Okay. Primary TUF is what do you mean by primary TUF? The primary of the transformer is feeding the two half wave rectifier separately. So primary winding is 2 times the TUF of the half wave circuit. And what is the TUF of a half wave circuit? We have found out 0.287. So it will be twice 0.287. So TUF for the primary winding will be 0.574. So the average TUF for a full wave rectifier will be TUF of the primary and TUF of the secondary divided by 2. That is 0.812 plus 0.574 divided by 2. That will be 0.693. So 69.3% your transformer is efficient in case of a full wave center tap rectifier. Okay, so write down this final answer. Why we consider both the cases? Because primary current is full and the secondary is divided into two parts. That's why we take the average of both. So that means which is the best rectifier? Whatever you have studied, bridge rectifier. Now I can ask you one last question. Compare half wave rectifier, full wave center tap, full wave bridge rectifier. So first point will be the circuit diagram. Second point will be how many diodes are conducting. Third point will be their output average formulas, output current formulas, output RMS, ripple factor formula, TUF formula. What else is remaining? Rectification efficiency form. I mean, it's different for all three. I mean, for two of them it's same and different for all. Then PIV rating of the transformer. That is also PIV rating of the diodes. They are also different. Okay. So with this we complete all the rectifier circuits which we have. All right. And we stop the lecture here.